I don't need to do anything on my laptop. Awesome. Yeah, thank you all for being here, and thank you so much, Shivam, for inviting me. It's really a pleasure to get to meet many of you in the math and stats department. This talk is on sample amplification, and it's going to we can keep it pretty informal. Feel free to stop me, ask questions, and yeah, we can go at your pace. This is based on two papers. The first one is with Brian Axelrod, Shivam, Garg, and Valiant, and the second one also includes Yanjun Han. So I'll dive right in. So the question that we are going to try to understand here is a pretty basic one. We want to understand when it is possible to make more data. So suppose you have some samples from some distribution that you do not know. When can you generate a larger set of samples, which looks indistinguishable to a larger set of samples drawn i.i.d. from the true distribution? And in particular, we are interested in understanding if it could be possible to generate this larger set of samples, even when you do not have enough data to learn the distribution. If you have a large enough set to learn the distribution, and it feels like you should be able to generate more samples. But could sampling be easier than learning? Could it be possible to generate a larger set of samples, even when you do not have enough data to learn? So learning by itself is obviously a task which has a long history of study in statistics, and we understand pretty well how much data is required to learn various distributions to various metrics. But in many cases, we don't necessarily need to learn the distribution. Perhaps the goal is actually to sample, generate more data from the distribution, and you want to distinguish between the complexity of these two tasks, if there's in fact a difference. To study this, we formulate this new problem, which we call sample amplification. Let me describe this. So sample amplification can be thought of as a game between two parties. You all can be the amplifier. You get a set of n samples drawn i.i.d. from some distribution d that you do not know. And your goal is to generate a larger set of n plus m samples. So increase the data set size by m. So generate some fake artificial data. So these might not really be samples. And what properties should these samples have? These samples should pass tests by any honest verifier. Let me explain what that means. Suppose I'm the verifier here. I'll get this set of n plus m samples. And I also know the distribution d. And I'm allowed to do any statistical tests that I want on this set of samples. And then I'll decide to either accept or reject these set of samples. I'll decide, is this actually a good set of samples, which looks like samples drawn from the underlying distribution D. I know the distribution again. And I promised you that I'm an honest verifier. So if the input is actually n plus m, i.i.d. draws from the distribution D, then I do accept these samples with good probability. Because otherwise I could just be like a bad verifier which just rejects every samples, then obviously there's not much you can do against such a verifier. But I promise you that I'm an honest verifier. I reject samples which are actually coming from the distribution D, and their i.i.d. draws from D with good probability.
If that probability relates to how many samples you are generating here, so it is immaterial here.
Only any constant would work here.
Bigger than 1/2.
Yeah. Any constant. Actually, there'll be another constant that'll come in, and those have to be related. But yeah, anything. Think of something bigger than 1/2. That's more than enough.
Sorry. Can we compare the value n over n plus m and this constant you give? Because if one.
Yeah, they'll be related.
Okay.
Yeah.
Go ahead. I was to say, and this is just a test for your verifier, because eventually the way you're going to generate your n plus m samples, you're not going to know if they're i.i.d., but you want them to be as much as possible.
Yes.
Right?
Yeah.
And in the future, you're actually not going to know d, right?
Yeah. So the verifier will always know d.
I see.
The amplifier does not know d. And you want to pass the test by this powerful verifier which knows the distribution.
And the verifier is in polynomial time.
Good. No, doesn't need to be polynomial time. Yeah. So right now, so the verifier is like basically as powerful as you can think of in some sense. So it knows the distribution D is computationally unbounded. But it does not know this training set, this original set of n samples that you got to see. So the setup is that you got to see this set of n samples. You train some model on this perhaps, and then you generate some larger set of samples. And then I, as a verifier, will evaluate this larger set of samples. I know the distribution D. I am computationally unbounded, so I can do any statistical test, even with something which might not be efficient. And then I will decide, my goal is to try to reject as many samples as possible. So it's a game between these two parties. And your goal is to try to make me accept these set of samples. So what you would like to do is generate some larger set of samples, fake samples, which do pass tests for any verifier, which is honest. Just as a side note, like even though these samples are supposed to be fake samples, this setup itself, this particular image itself is less fake in the sense that this was actually made by a generative adversarial network, which were all the vogue a few years back till diffusion model stepped in. And this can be all yours for a cool $500,000. This is actually the price at which it's sold at Christie's auction. So you can probably do, I don't know, do you pass or reject this sample? Depends on the entire set, but
Relative to the rest of them, for sure.
relative to the rest of them, I guess. Yeah. Yeah. So really, yeah, it's there is some distribution. In this case, I guess the distribution is over these Renaissance portraits, and then you want to generate a larger set, which looks like samples from Renaissance portraits. And if you can do that, we say that you can amplify this class of distribution. So let me define that more formally now. So we say that some class of distribution C admits n to n plus m amplification. If there is an n to n plus m amplifier, what does this amplifier do again? It takes a set of n samples and generates a larger set of n plus m samples, such that for any distribution D in this class, any verifier which is honest will accept these samples with good probability. Probability at least 2/3. And these two constants can be arbitrary, essentially like you'd want it to accept with some probability, which is as close as possible to the probability with which it's accepting samples which are actually coming from the underlying distribution. And the randomness here is like this probability is over the randomness in the training set, over any randomness in your amplifier, and any randomness in the verifier. So this seems like a pretty natural problem in itself. It's understanding when you can generate a larger set of samples. It's also pretty related to trends that we're seeing in machine learning, in the sense of becoming more and more popular to try to increase the size of data sets to help benefit downstream algorithms. So the more classical techniques of this form are just data augmentation techniques, where we add some images or transformations which respect known invariances in the data. For example, maybe translation or rotational invariances. More recently, there's been a lot of interest in augmenting the size of data sets by generating artificial data with generative models, previously GANs, now diffusion. So for example, this is some fake X-rays created using some diffusion models. And this found to be particularly useful in domains where we don't have enough data, often like medical domains where it's not possible to access so much data. It's been a lot of interest from the applied community to try to use these big generative models to increase the size of data sets and maybe benefit downstream algorithms. This is another example of like some facial recognition tasks where like Microsoft, instead of training on real data, they train on these artificial images, sort of cartoonish images. And they get comparable accuracy. And another claim that they make is that they can preserve privacy because they're not trained on real data itself. Something, another advantage which could come about from trying to learn on synthetic data. So it's not clear to what extent things will be private. And then there's like a whole suite of techniques which are more opaque. One technique which is very effective in practice is to take two samples and do this weird thing where you superimpose these samples. So this is, if you have a cat and dog image, cat versus dog classification task, create a new image, which is 50% dog, 50% cat. So the technique is called mix-up. Somehow, weirdly enough, this helps.
This is not a pixel level like a superposition, right? So it's some.
Yeah, it's actually just taking half of this and half of this. It's really just pixel level. Like this mix-up is all that does. Like I guess it's not really probably clear on the projector. There's a dog hidden inside this image. Like, I think the cat image is more prominent.
Has a darker background, so.
Yeah.
So does this mean the label should be cat instead of dog? Or
So the label for this new artificial data point would be 0.5 cat, 0.5 dog.
oh, I see.
It's quantum.
Sharan cat. So yeah, and then there are like techniques where you crop out parts of images, put in like a parts from another image, or erase some parts of images. It is like zoo of techniques, and which in general they seem like quite popular. So given the success and like interest in these techniques, it seems natural to try to put them on a firmer statistical grounding. And that's one goal here, to try to formulate this setup, which we think provides a natural starting point to understand when you can generate a larger set of samples. And, we'll go back to like how these samples might be used and how we can think of this in our framework towards the end of the talk. Let me go back to a definition now. So we, again, just to remind ourselves, we have a class of distributions. We say it's admits amplification. If there's an amplifier which generates a larger set of samples, such that any verifier will accept these samples. To make sure we understand this, let's just look at a few properties of amplification. First, I claim that every class of distribution C admits n-to-n amplification. Does anyone want to take a guess of why this is the case?
Random permutation.
Random permutation of the training set. Yeah, it's actually even simple. You can just pass the training set. So the verifier does not know the training set. And the verifier is honest. So it has the promise that if you pass samples which are actually i.i.d. from the true distribution, then it will accept those samples. So if you get this training set, if you just pass me back that training set, because that training set was n samples i.i.d. from D, I will accept those samples with good probability. So n-to-n amplification is trivial just because of like how we are setting things up over here.
Sorry,
Yeah, ask a question. Yeah.
Why is it still independent? I get lost.
Why is it independent? Because the original training set in our setup, go back.
It's not joint independence between the two sets, right? It just each individually has to be i.i.d. with the distribution.
Yeah.
So if I give you a set that's already i.i.d. with D, it's still going to be i.i.d. with D. If my verifier is good, it should do the same thing because that's how I defined it, right? To work well on an i.i.d. from D distribution set.
And the crucial thing is that this verifier does not see the training. So if it saw the training set, then like it can obviously, it's easy for it to decide when to reject if it's the same as the training set you reject. But the verifier does not see the training set. You get the amplifier, you get the set of n samples.
So it's m plus m. So you mean m equal to
Is
0?
zero.
M equal to 0.
I saw
yeah.
m equal to
Exactly.
n.
Oh yeah.
Okay.
Yeah. No new set of samples. Yes. Good. Yeah. That's just that's how we're defining.
There are a lot of words here, so.
Yeah.
I saw the m equal to n.
Okay. And the verifier does not see the amplifier's n input samples. And if the verifier did see the set of samples, and if you had to generate a set of n plus m samples, which were good condition on like this training set of samples, then this setup would be equivalent to learning. And the only way to do that is to actually learn the distribution and generate a set of samples which are close in total variation distance, say, from true samples from the distribution. So it's crucial here that the verifier does not see the amplifier's training samples. And up to constant factors, this game between the amplifier and the verifier is equivalent to asking if the amplifier can output a set of n plus m samples whose total variation distance to n plus m i.i.d. samples from D is small. This is really the definition of total variation distance. It means indistinguishability under any statistical test, and the verifier can do any test here. So maybe like up to like how you choose these constants, like you will get some TV distance which is also related to these constants. So like the goal, like if it's easier for you to think of it that way, you can just think of you're getting a set of samples and your goal is to generate a larger set of samples which are close in total variation distance to the larger set of samples drawn from the true distribution T. And they're close in total variations. And just a few more points, like especially for like this one for people from a TCS background, perhaps. So like this two-player setup might reminiscent to a pseudo-randomness setting. Where in pseudo-randomness, we say that you have to generate some sequence of bits which look like random to any verifier. But there, like crucially, we have to say that the verifier is computationally bounded in order to fool that verifier into thinking that this actually pseudo-random sequence is a random sequence. And here, like in our setup, there's no really, like in pseudo-randomness, it's crucial, like the crucial resource of the amplifier is how many training truly random bits it has. So here, like there's no limitation on how much randomness the amplifier has. Basically, it's a training set. So there's no resource limitation in terms of how much extra randomness you can use. And finally, more on the statistical side, it's actually equivalent to a statistical notion called Leckam's distance. And this is like sample amplification, the setup is really the same as finding the best Leckam distance and any transformation between the product distribution on n samples and the product distribution on n plus m samples. I won't really define this because it's not necessary for the rest of this talk, but just as a note, in case you've seen this notion and if you want to look more, you can look at the paper. Are there the questions about the setup? So I'll start to talk about some results now, but yeah.
In practice, is D usually discrete?
We'll talk about both discrete and continuous distribution. Yeah. Okay, so let me talk about some results. We'll begin with really like two results which try to investigate if amplification is even possible without learning, starting with the discrete case first. So let's see this class of distributions be discrete distributions supported on at most k elements. Then we say here that n to n plus order n by square root k amplification is possible. And that this is optimal up to constant factors. So let's understand this. This means that you're generating n by square root k additional samples. So you started with the set of n, and then you're generating you're outputting n plus n by square root k. And this is also optimal. You cannot hope to do better than this. So this is saying that you can start to do some non-trivial amplification. You can amplify by at least one new sample. As soon as you have about square root k samples, because the number of new samples is ordered n by square root k. Whereas learning discrete distribution supported on most k elements to any non-trivial accuracy, or to any metric really, would require about k samples. Because you need a k samples to even see most of the support of the distribution. So we're saying that amplification can indeed be easier than learning. So generating a new larger set of samples could be easier than learning. But also know that you can never really amplify by an arbitrary amount in this general case at least. So even if n is much larger than k, the best you can do is n by square root k, because this is tight. There's a lower bound saying that that's the best possible.
Is there an intuition on square root of k?
Yes.
Okay.
Yeah.
And you're going to share.
Yeah. I'll talk about this setup. I think the algorithm here is very simple. So I'll talk about the setup in reasonable detail.
And so the intuition is essentially constructed.
Yeah. Second one is a class of continuous distributions. So it's even the class of Gaussians in d dimensions with some fixed covariance. You can just think of this as the covariance being isotropic. The covariance is fixed and known, but you don't know the mean of the distribution. Then n plus n by square root d amplification is possible. And this is optimal up to some constant factors. So again, let's understand the message here. Saying that you can do amplification with only about square root d samples. Whereas learning, again, to any non-trivial accuracy, learning the mean of Gaussian in d dimensions would require about d samples. So you can generate new samples before you have enough information, enough data to learn the distribution. So amplification could be easier than learning, and it is easier than learning in these cases.
The Gaussian essential here, or we can do like lighter tails like sub-Gaussian or no.
Good, good. Yeah, that's a good segue into the next classes of results. So we consider some broader classes too. So we consider exponential families. So Gaussian is a special case of that. So let's see with the class of exponential family, any exponential family in d dimensions. I won't really define it. That's class of distributions which includes lots of common and natural distributions. So let's see exponential families which have continuous distributions. And on a technical note, they need to satisfy a certain moment condition, which most continuous distributions seem to satisfy. Then we show that you can do n to n plus n by square root d amplification again. This is optimal up to constant factors.
So this exponential family is a full exponential family, or you allow the curved exponential family with some constraints on the parameters?
It's a full exponential family.
It's full.
Yeah. So it's full exponential. You can do like in d dimensions, you can do n plus n by square root d.
The moment condition is just to ensure that things are well behaved. Right?
Yeah. So the moments that exist, and that's.
I'm thinking about the curved case because the implicit dimension for the exponential family in that case depends on how many constraints you have. So in that case,
it could probably shrink. Yeah. So we consider like sparse Gaussians. I'll talk about that a little bit too. Later, hopefully, I'll talk about some class of techniques which give these results, and that give some results which don't exactly fit in within this too.
And do your moment conditions ensure that in each dimension, things don't really dominate more than another? Like before you had the isotropic condition, which you don't have here.
Yeah. So in this case, it's really about moments existing. So I guess, it's all like for some k, which is like 10, like all these kth moments exist for the distribution. That's really what we require for this. And I guess, but it doesn't need to be some relation necessarily between moments in certain directions. It's about existence of those.
So if I were to take the Gaussian case, I could have a not great condition covariance matrix and you would be okay.
Yes. Yeah.
So basically the big O constant is hiding some sharpness of this kind of conditional number due to this high order constraints, right?
Yeah, so this big O actually, so in this case, like for this general class of exponential families, even so maybe I'll talk about how we do this. It's via some CLT results, but these results suffer from some dependence in D. Like we don't really know the best dependence on D, like dimensionality. So this really holds for sufficiently large n. In order to actually say that you can amplify with square root d samples, we consider a class of product exponential family is really the same thing, where you have along every direction you have the same exponential family which is continuous and satisfies the same moment condition, and then we can get n plus n by square root d amplification along all directions for all n, and it's also optimal as it was before, and this the same message as the previous slide, showing that you can do amplification with only about square root d, whereas learning for these exponential families in d dimensions would require about d samples. So you can do amplification before learning for this larger class of distributions. And beyond these, we also consider bunch of other distributions. So so far I talked about this Gaussian with unknown mean and fixed covariance. I talked about discrete distributions with support at most k, then these exponential families. We can do a Gaussian with unknown mean and covariance. So it's both mean and covariance being unknown. That's falls within exponential family, but it's not a product exponential family. But we show a special result here that you can actually do amplification for all n. So you can do n to n plus n by d amplification. So d squared is like the dimensionality here because we're looking at an unknown covariance. And a trend that you'll notice across all of these results is that you can start to amplify at square root of dimensionality. At least across all of these, that seems to be the case. So you can amplify at n by d over here. This Gaussian with the s sparse mean and just identity covariance. So mean has only s non-zero entries. There you can do amplification at square root s log d samples. So like given square root s samples, you can start to do amplification. So essentially the effective dimensionality becomes s here up to logarithmic factors. And you can do like products of exponential distributions, Poisson distributions, and the uniform distribution in d dimensions. And for all of these, you get this like n by square root d amplification. So you can increase the number of samples by this factor. You can start to amplify with square root d samples. And all of these are also tight. We show minimax lower bounds that for each of these classes of distribution, this is the best that you can do for that class. So I'll talk about, I'll start with just the Gaussian, like the discrete case first, and then the Gaussian case, and then I'll talk about some of these, like the more general frameworks which give these other results. But are there questions about like statement or setup before we do that?
So the d-dimensional product of the Poisson, so you basically take the tensor product of the 1D Poisson, or it's a...
Yeah, it's a tensor product. So along each coordinate, it's a Poisson distribution.
And then in this case, if I think about a d equals 1, then that's a discrete case, but your support is not bounded by k. So how do I understand with the previous, bounded support bound?
So like if you have, so in this case, we are looking at the support of k. Like if you just have d equals to 1, I guess like this would just say that you can amplify. This is like saying that k is equal to 1 in this case, I guess. So you're just saying that you can amplify by.
For some cases, d equals 1, right? So you have
Yeah.
roughly 2n or maybe.
Yeah, you can amplify by 2n, but again, this is like a.
In the bounded case, you simply to amplify less, right? So you have to.
Yeah, because the support, like there's a unknown support of size k here. Like when you're talking about a Poisson,
so
it's
you have
really
to
like
sort of
just a number.
estimate the support
of
the distribution, which is
Right.
actually the
Yeah, that's the
dominant
dimensionality there in some sense. Yeah. That like you need to know something about the support. That's the thing which dominates. Any other questions?
Just clarifying, all those amplification results based on the lower bound theta and function. You have your initial sample greater than some lower bounds, and enough information allows you to do the applications, right?
So these are all like, this is saying that you can, these are like theta, so like up to like some constant, you can do n to n plus constant times n by square root log d.
Okay, and
So that's what this result is saying.
The lower bound theta permits non-trivial application.
Yeah, so they're not like up to some, like suppose we like say the discrete result, we show that you can do n plus c1 n by square root k, then we show a lower bound that the best is possible is n plus c2 n by square root k, like for some other constant c2, which obviously would be more than c1, otherwise the result would not be true. Okay, so let me talk about give some more intuition here. So I probably spend most of my time talking about the discrete and the Gaussian case and hint a little bit at the more general frameworks. I'll start with this discrete distribution. It's a very simple case. So suppose we have just a uniform distribution, but we don't know the support of the distribution. The distribution is uniform over some unknown support. It's the support of the distribution. Now, first let's see why you cannot do amplification when n is smaller than square root k. Suppose n is much smaller than square root k, and you get this set of n samples, then with high probability, no element is going to appear more than once in this set of samples. I think that you can verify. And because of this, there's no hope of doing any amplification here. Because to produce n plus 1 samples, you would have to produce an unseen element, and you do not know the support of the distribution. So there's no way that you can add a new element because you don't know what else is in the support. So because of this, you cannot do amplification if n is much smaller than square root k. Now let's see what happens when n is c times square root k for some constant c.
Wait, for the first regime, why can't you just add the C1?
Why can't you just add the c1? Because no element should appear more than once with
Oh,
high
sorry.
probability. So the verifier will just check
Okay.
if there's something repeated,
All right.
and the verifier knows that, hey, there shouldn't be anything repeated with very good probability. So you just reject all samples which have repetitions. Now, when you have n equals c square root k examples, now you expect to start to see repetitions by the birthday paradox. And in fact, you can show that the distribution of the number of things appearing twice has mean about c squared by 2. So you expect to see about c squared by 2 repetitions with c square root k samples, and with standard deviation order c. So then amplification is not, it sort of follows from this. So you consider an amplifier which duplicates any of these elements which only appear once in this set. So I take, suppose this particular element, duplicate it, and then randomly shuffle all of these samples. Now I've increased the number of repetitions by 1, but there's this variance of C expected in the number of, the standard deviation of C, variance C squared, expected in the number of repetitions. So if I increase the number of repetitions by 1, that the verifier cannot really detect that with good probability. So in this case, if you just increase this, like take something which appears once, duplicate it, then the verifier will accept this set of samples with good probability. And that's basically the amplification scheme. For the
So
special
that standard deviation depends on how large you choose this constant C.
Exactly. So that's why the number, the amplification, the standard deviation is C. And that's why we can do amplify by about C samples. And that's consistent with the result because it says that you can do n by square root k, which is C in this case. And the general scheme for Gaussians is very similar to this. You just draw m new samples from the empirical distribution of the original n samples. And then you return a random permutation of the original n samples and this new m samples that you generated. We can show that the distribution of the return set is close in total variation distance to n plus m samples drawn i.i.d from the distribution T, which gives us the theorem for the discrete case. And we'll see later that actually this sort of amplification by learning the distribution and shuffling is more general than the discrete distribution as well. Yeah.
I don't get why we have to do random.
Oh, if you don't do random permutation, then if you just repeat this sample right next to it, then that's also easy to reject, right? Suppose the verifier rejects every sample which has a repetition like next to each other, like if there's a repetition like in consecutive elements.
Means it's not i.i.d.
Yeah, then it's obviously, yeah, it's if you draw i.i.d samples, then the probability of getting a repetition in continuous positions is pretty small. So. Okay, so let's talk about the Gaussian case. If no more questions about this. So let's recall the theorem for the Gaussian case. We see that indeed Gaussians in d dimensions with some fixed covariance and unknown mean. You can amplify starting at square root d samples, whereas learning requires about d samples. And you can do n to n plus n by square root d amplification. In the previous case, we kept around the original set of samples, generated some new samples, and then shuffled things together. Can we hope to do something like that over here? Keep around this original set and shuffle things together? Actually, no. So we show that if the output set is the superset of the input set, so if you keep around all of the original samples that you got, then you cannot really get this result. You require d by log d samples to even amplify by one new sample. Whereas like it's actually possible to amplify starting at only square root d samples. So even though the verifier does not see the training set, if you keep around the training set and do anything else with the additional samples, you cannot hope to do this optimal amplification. you would basically need almost D samples, what is required for learning in order to do any amplification. Intuitively, the reason for this is that if you keep around the original set, then these new set of samples would just be too correlated with the original set of samples. So by a picture, if this is what the amplifier passes to us, even though we don't know anything about the training set, what was actually in there, we can detect that there's just like these images are too similar. It wouldn't happen if you were actually getting i.i.d. samples from the distribution of portraits. And you don't need to know the original training set to detect these correlations. So the algorithm here first draws a new set of samples and then applies a decorrelation step to remove the correlations of this new set of samples from the original set of samples. And then it returns a list of just the original samples and the new samples.
What is the noisy version of the empirical mean? What do you mean by that?
Right, so just like sample from a Gaussian with mean, mu star, and covariance, whatever is the covariance of the Gaussian.
You know that, right?
Yeah, we know the covariance. That's what
Like a bootstrap, this procedure.
Yeah. So you sample like from the estimate, and then you need to do a decorrelation step, modify the original samples because otherwise it's not possible to do the optimal amplification.
And so when you say decorrelate, you're like projecting into like the null space of U star? Or
Projecting in a certain direction. Maybe I can talk about that quickly. So like essentially what we do is suppose in 2 dimensions, we sample 3 examples. And then if I generate a new sample from the empirical distribution, the issue is that this new sample is just too correlated in the direction of the mean of the original sample. The projection is too high. So what we do, ignore like all the math. Essentially, what we do is just move all of the original samples in the opposite direction of the new sample. So it's just a shift applied, like in the same direction to all of the original samples. And this gives you this optimal amplification.
Why is that? Accomplish the same thing?
Can you
A rotation that doesn't accomplish the same?
a rotation of just the original samples, or like rotating everything? Rotating everything wouldn't do it because like you'd still have correlation in that direction. Like this thing that I said over here, even if you rotate the figure, it's still the same issue. If you just rotate the original set of samples,
No, the new sample and will still have the same relationship, right? If you're rotating the original ones. So it's not solving that.
yeah. You wouldn't
Just
really.
pattern matching. They say on the circle, right?
Okay, so how are people feeling at this point? Like, should we talk about some more general frameworks? Do people have questions about what I talked
Why
about?
is the perturbation is 1 over n for each point in the training?
Why is the perturbation 1 over n? Because that's like related to how much correlation there is. Like the projection, like instead of being like 1 over square root n, say, like you would want, it makes sense that it's inverse, and like the larger n is, like the less you want to shift. But I guess your question is, why is it not like 1 by square root n? I don't know if there's a great answer from that other than I think that's the amount of correlation there is. Like the way that we like did this is just like if you look at the covariance matrix and you try to try to come up with a transformation so that the correlations are 0. This is what comes out. I think it's related to how much projection there is in like that direction, but I don't know if there's a great intuition beyond that. Think more about that later.
Should be, it's Gaussian, there should be geometry, right?
Yeah. It's probably there should be, and actually we'll see that there's actually more general ways to do the Gaussian result as well. And I think in ways which I think are some sense cleaner too. So let me talk about some more general frameworks. So it's 20 more minutes, right? Including questions at the end.
4:30.
4:30. Okay. So here's like two more general techniques rather than these two particular algorithms that we saw. The first one is amplification via sufficiency. Here you generate n samples, find their sufficient statistic. This assumes that there is some sufficient statistic. Then you generate a larger set of samples, condition on the larger set having the same sufficient statistic. I'll describe this more soon. Yeah.
Do assume the distribution has some sufficient.
Yes, for this procedure, there needs to be a sufficient statistic.
Oh, okay.
So yeah. So and I'll talk about this more in like just a minute. Let me just mention the other one too first. The other one is more like the discrete distribution sampling case, where you learn the distribution, and then you generate m new samples from this estimate, and then output a random permutation of the old and new samples. This is exactly what we did in the discrete distribution. For product distribution, the additional thing you can do is that you can apply the permutation independently on each coordinate. So instead of doing the same permutation across all coordinates and permutation on this set of samples, you can apply an independent permutation on every coordinate. And that is necessary to give the optimal amplification. So it's these two techniques together give all the results in the table that I showed before. Let me talk about both of them in a little bit more details. Let's start with the first one. So you estimate the sufficient statistic here, assuming that there is sufficient statistic. Then you generate a larger set of samples, condition on them having the right sufficient statistic. Let's see this just for the case that we saw before. So let C be the class of Gaussians in D dimensions with some fixed known covariance and unknown mean. It's exactly the setting we saw before. Use another algorithm which gets the same guarantee. So you learn the empirical mean mu hat, and then you draw n plus m samples, condition on them having mean mu hat and having covariance sigma. You know the covariance here. This is in the fixed covariance case. Let's understand this algorithm. First, notice that it doesn't keep around any of the original set of samples. It's generating an entirely new set condition on having them having this particular mean. And that is necessary by the theorem we saw before. If you keep around the original set, then you cannot be an optimal amplifier.
In statistics, this procedure is instead of called amplification via sufficient statistics, it's called parametric bootstrap.
Parametric bootstrap. Okay,
Yeah,
that's good. Yeah, yeah, we should discuss that more. So yeah, you just keep around the sufficient statistic and generate a large set of samples. And this gives like this Gaussian result, the exponential families, and the amplification for the unknown covariance case, product of exponential, product of Poisson, and the uniform distribution. So like on the computational side, in order to accomplish this, you need to be able to generate this new set of samples, condition on them having this particular mean. And that's not difficult to do for various exponential families because there are often ways to do this. Like one nice technique is via these ancillary statistics. So these are statistics which are independent of the modern parameters. And using the sufficient statistics and the ancillary statistics together, you can recover the original set of samples. So what we can do is you can sample these ancillary statistics using any distribution in your family, and then use your sufficient statistic and the ancillary statistics to generate this larger set of samples. Let me give an example again for this case. So first, you generate n plus m points. The goal was to generate n plus m samples, condition on having this mean mu hat and covariance sigma. So you sample n plus m points, call these xi, from Gaussian with mean 0 covariance sigma. And suppose they have empirical mean x bar n plus m. And let si be xi minus the mean of these samples, the empirical mean of these samples. And you can show that this is actually an ancillary statistic. So together, if you know the sufficient statistic, the mean, and if you know the ancillary statistics, and obviously you can recover the original set of samples because the sufficient statistic here is just the empirical mean. And to generate this new set of samples, you just take the empirical mean mu hat of the original set of n samples and add together these ancillary statistics for n plus m samples that you computed. So this will ensure that they have mean exactly mu hat because the mean of SI is 0 just by construction. And you can show that this condition on them having mu hat, these look like samples drawn from n plus m samples drawn from a Gaussian with covariance sigma.
Do you need independence between the ancillary statistics and the sufficient?
Yes, yeah. So these would be independent. So like in this case, you can show that like the ancillary and the sufficient statistics.
Yeah, this will be independent plus actual conditions if you focus on exponential family. So you do need actual like completeness of this.
in order to
this to be independent, you know.
Okay, that's yeah. Actually, we were thinking if there's a we showed this for all of these distributions we considered. We were wondering if there's a characterization of when this kind of process exists. Maybe we can talk more. And it could be a characterization of when you can actually do this efficiently too. So, and in terms of how we show this, like let's say if you consider the class of exponential families, what we show is that basically the sufficient statistics will be close to Gaussian by central limit theorems. And then you can say that because condition on preserving the sufficient statistic, we have the distribution looking like, we have the samples looking like n plus m samples drawn from the right distribution. Therefore, you are close in total variation distance to a true set of samples. So mathematically, like what you want to show is that the distribution of sufficient statistics on n samples and the distribution of sufficient statistics on n plus m samples, like we will bound the total variation distance between them. And then we'll do that just by using triangle inequality and using the Gaussian CLT results. So we'll first show that the sufficient statistic is close to Gaussian. Then the Gaussian on n samples and Gaussian on n plus m samples are close. And the sufficient statistic on n plus m samples is also close to a Gaussian. And you apply some CLT and CLT convergence results to show this. We won't talk more about this. We can talk more offline. In the next technique is like amplification via learning. So here, as we just said, you learn the distribution, generate m samples from the estimate, and then output a random permutation. And for product distribution, you apply this independently. And for the Gaussian case, again, what this would mean is that you just generate m samples along every coordinate from the covariance that you know and the empirical mean that you estimated, and then shuffle everything together. So shuffle every coordinate independently and shuffle the n original samples and the m new samples independently across all of these coordinates. So one good thing about this is that actually gives a relation between learning and amplification. So when like it and helps understand when amplification could be easier than learning. So what we show here is that suppose we learn the distribution to some chi-squared divergence epsilon, then you can amplify by square root n by epsilon samples. You can generate an additional set of square root n by epsilon samples. And just by this procedure of generating new samples and outputting a random permutation. And you can do something better for product distributions. Right? You just have to estimate it for every coordinate. Main thing here is that this means that it suffices to estimate to chi-square distance about n in order to start to do some non-trivial amplification by one sample. Whereas generally, like in the sense of learning, you would need to estimate to constant chi-square divergence in order to be able to output a sample which is close in TV distance to a true sample from the distribution. So it sort of like explains why amplification can be easier than learning. So if you can estimate to chi-square divergence much fast to like by some epsilon, then you will be able to amplify much earlier than you are able to learn.
Should my amplification be in service of learning?
Okay, yeah. So that's I think a great segue to like talk about like when amplification is actually useful. So like when can you actually use this? So amplification does not add any new information. Like you you're taking this original set of samples and generating a new set of samples. You're not adding any new information. The amplifier is not doing anything interesting information theoretically. However, it could make the original information more easily accessible. What do I mean by that? There's lots of statistical tools and heuristics that we use, which are not necessarily optimal to begin with. So we don't always use optimal algorithms. There's various other considerations like simplicity or efficiency. So could it be that like the tools that we use more often actually do better on an amplified set of samples instead of when they are fed the original set of samples? Could amplification make things easier to learn? I think that's generally a very good question, which I'm very interested in understanding. It is a very small toy experiment to maybe illustrate why it could be useful. So suppose we have samples, X, Y, so labeled examples. And the goal is to estimate the error of the best linear model on this data. So the learning task is to find the fit of the best linear model, the best way to predict Y using a linear prediction on X. Obviously here, the standard unbiased estimator is just to fit a least squares model and then return the error of the least squared model with some appropriate scaling in order to make it unbiased. So let's consider this experiment. Now, suppose we have Gaussians in 50 dimensions, and we generate the labels via a linear model, add some Gaussian noise. So the goal here is just estimate the variance of this noise. That's the error of the least squares model. So this blue line is the classical estimator. So you do a least squares fit and return the error of the least squares estimate with some scaling. And the yellow line is the same estimator when it is fed an amplified set. So when you feed in like 2 additional amplified samples. And what you can see over here is that in the regime where the number of samples is very close to dimension, like this, the feeding in this amplified set of samples helps this estimator by a little bit.
And the definition of sample size for amplified is +2.
+2, yes, yeah.
So you get a better so-called learning rate. Your ultimate mean squared error is not, asymptotic mean squared error is not going to change.
Yeah, asymptotically nothing is going to change. But we see that when you number of samples very close to dimension, you get a benefit. Like this estimate is a classical estimate. This is not optimal. So we're not violating any minimax lower bounds in the sense. So it's known that when a number of samples is very close to dimension, there are better ways of doing estimation. But this very simple one does benefit, and it does much better when the number of samples is like really close to the limit at which it works.
Sorry, this least squares minimax, right? So you said or not?
This error of the least squares model?
Yeah, just this model, the linear.
This is just a particular setting. There's no, like, we're not doing
So
like
you're
minimax.
not
across.
changing the parameters.
No,
it's
no,
just
no.
pick
Yeah.
up this.
Yeah,
data.
it's just like this is the simulation. That's all.
What
we
does the data looks like? In this case,
We sample data from another Gaussian.
Oh,
Yeah.
random.
Yeah, sample data from a Gaussian.
I think I might be missing something. In this case, things are matched, right? Like if you have Gaussian observations, then linear is the right way to go.
So this is an unbiased estimator. This is not the best estimator. So there are estimators which have smaller, which are biased, but have smaller variance. In some sense, that's what this is. Amplification is also mimicking, I think. It's adding some bias, but lowering the variance.
Yeah, so that's I'm curious. How do you pick the theta? If theta has a few like non-zeros, then you can just apply shrinkage, James Stein style.
Yeah, I think
thing,
shrinkage would
and just do the pointwise improvement, right? So
yeah, shrinkage would help here. I think like what the point here really is not that.
so is this amplified kind of estimates has some implicit bias?
No, but I think the question is, if you took a shrinkage approach, would it do better with the amplified data or not, right? That's the issue here.
Right.
Not the quality of the estimator, but the boost that
Yeah.
it gets from using amplified data.
Yeah. So in general, like also like any optimal estimator cannot benefit with amplification.
Right.
So if you're doing the optimal thing to begin with, like
You're
by
not.
definition, like you cannot benefit from
Okay.
amplification.
Yeah.
So like it's really like when you look at things which are suboptimal, could they benefit from doing
I see.
amplification?
Yeah.
So obviously like it's a very like toy setup where I think this happens, but I think it'd be very interesting to try to understand when this is true more generally. So can you design this sort of modular frameworks where you have an amplifier which generates more data and then you learn on this larger set of samples where possibly by using simpler techniques or techniques which don't really take the data distribution into account. I said before, like there's already like a lot of interest in doing things like this. So this whole company, probably bunch of companies, Synthesis AI, the goal is to develop better models, deploy it faster with synthetic data, whatever that means. And yes, I think checking has like a valuation of 100 million or something. So for better or worse, I don't know if this is a good sign or a bad sign that.
It's weird though, because these, AI generated faces are very creepy.
Yeah. Yeah, I guess like, but one thing which I think even like this Microsoft thing where they trained on these AI generated faces, even though the faces might not be super realistic, they might still benefit, like a model might be able to still learn from it. And actually, in some cases, they've shown that the model might be better because the sample set is more diverse. Because it's like, I think one problem, and I think there's been lots of studies like this, like gender shades, where it's really hard to generate, to collect like a nice representative set of samples. And that sort of thing might be easier with synthetic data. So I think
with this how amplification is robust to, for example, adversarial perturbations in your training data, do you have any?
I don't, yeah, I think like in some of these techniques for training models which are adversarially robust to like augment the data set, but they augment it in a way which is model dependent. So for any model, they'll add some perturbations which will make that model better. But I don't know if generally it would, I'd be surprised if it helps for adversarial robustness, because adversarial robustness is just hard because I don't know if like just by doing augmentation, like this amplification, you can help any downstream algorithm, like which in a way which doesn't depend on how the algorithm is actually running. I think it's probably easier to benefit just like generalization or out of domain generalization, things which are more average case. Yeah, I don't know if this is like, if we can actually show this formally. Again, more general, I think like you could look at different, lots of variations of the setup, like this really like the most basic thing that one could start with, like what we talked about over here. For example, you could just consider non-i.i.d. data, like what about amplification for like say text data, like data generated from some Markov model.
Yeah, exactly. That's why I wanted to ask, or even if you pick something simple like AR1,
Yeah.
you know.
Yeah, I don't know if you, when like you can take n sequences sampled from an AR1 process and generate n plus n
I mean, if
sequences.
it's easy to whiten, you should be able to go back and forth, right?
Right.
But Markov chain, yeah, I'm very interested in that.
Yeah, I'd love to chat about. Yeah. And you could also consider variations. For example, you could consider like, this is really like one setup that we talked about here. I think in many cases, it might be more meaningful to change the power that is available to the verifier. For example, you might want to give it more power. So how much would it need to know about the training samples in order to preclude amplification without learning? So right now we said that the verifier does not see the training set at all. So how much do we need to know about the training set to make sure that like any amplifier cannot do amplification without actually learning the distribution? In some sense, how much do we need to know about how, say, a generative model was trained in order to evaluate whether it's actually learning, it's actually learns the distribution instead of amplifying or cheating in a certain way? You'd also consider less powerful verifiers, which I think are quite meaningful for these downstream use cases. You could consider verifiers which don't actually know the distribution D, only get sample access. So when you think about how you might use something like this downstream, the verifier is really the downstream learning algorithm. You're feeding in the samples to this verifier, which would be the downstream learning algorithm. And if this downstream learning algorithm cannot tell the difference between a true set of samples and a larger set of samples drawn i.i.d., between a larger set of samples drawn i.i.d. from the distribution and this fake set of samples, which is also large, then this verifier, by definition, it should do as well on this fake set of larger samples as it would do on a true set of larger samples. To do something like this, like the verifier shouldn't know the distribution D, like the downstream algorithm shouldn't know the distribution D. And you might also want to consider computationally limited verifiers. Might be that you could do much more amplification for limited verifiers, which might mean that you can do a lot more to benefit downstream algorithms. Guess I'm basically out of time, so let's stop at this point. Happy to take any questions if you want to stay around.